Here's a video prep for exam one. And this is, of course, covering two different things, distributions and probabilities. Well, it'll be covering more than that. It'll cover everything basically from the beginning of the semester, or beginning of our course semester. But I'm going to focus on some problems because those are what most of you probably want to work on. So let's start with some practice problems. This is from third week of classes. Some of you may not have gotten here yet, but you should review everything before you get here. So this is a percentile problem. If you recall, percentiles are the percentage of individuals that are at or below a given score based on what we know about the population. In 2023, the mean and standard deviation SAT math score, excuse me, was 531, 111. So remember, the standard deviation always is within parentheses. Following the mean, a random Pennsylvania student scored 537 on the math test. What's her percentile score? So what's the probability that a student scored above her? So those are two separate questions here. What's her percentile score? So if we look here on the right in my beautiful handwriting, by the way, I'm working on getting a tablet where I can write in live time because that's what I really want to do. And that should be coming soon. So we have our population mean, that's the Greek letter, is 531, and the standard deviation sigma, Greek letter sigma, is 111. Our X value, or her score, is 537. Her percentile is the probability that X, the score, is less than or equal to. So X is basically the variable, and this is her value on X. But when we say what's the probability that X is less than or equal to 537, actually should be a capital X. This is a little x, right? Because that's her score. That's one value. Capital X represents the variable. What's the probability that the variable is less than or equal to 537? So we plug this into the Z equation. This is basically, we're standardizing this and putting it in, transforming this score that's in SAT units into a score that's in standard deviation units. So what I mean by that is standard deviations from the mean in a standard normal distribution. So it's 537 minus 531 divided by sigma, and we get 0.054, 0.054. So let me pause. I forgot I need to get out the table so you guys can see that. Hold on. All right, I'm back here. So here I pulled up the table. Boy, it took me a while to find that. So if you recall, our table is only half of the normal distribution table because you can get tables that have the full distribution, including the left side and the right side. So you notice that all our z values are positive, so we're only focusing on the right side. You can say, well, why the heck did you do that? It could have been so much easier if you just gave us the whole thing. Well, when you get out into the real world, do whatever you want to do, but this is actually better for you to understand the distribution because this distribution is symmetrical. Like if we fold it above about the mean, it'll be perfect matching of both sides. So you really don't need the full thing. So let's go ahead and take care of our business here. Let's go take care of our business. Where were we? I think we were right here. I was showing you our answers. Okay, so we get our z value of 0.054. So the same, here we ask what's the probability that x is less than or equal to 537. That's the same as saying the probability that z is less than or equal to 0.054. Now I have here, what's the probability that z is between 0 and 0.054 because we know that we only are using half of the distribution. But we really don't need any more information. That's sufficient, right? Because we know the probability of being less than or equal to 0 in a standard normal distribution is 50%, right? We did the empirical rule, so we already know that. So we don't need any more information than that. A lot of things in statistics are so intuitive. Once you figure things out, it's like, oh, okay, I don't need to really worry so much about anything. So the probability that z, and also you'll notice that I did 0.05 instead of 0.054. That's because of the way the table, and this is how all tables are done. You only go to two decimal places, right? So 0.050, right? So the way you read this is that we go 0.050, this would be 0.050, 0.051, 2, and so on. So we were looking for a value of 0.050, technically 0.0504, which we round to 0.050, right? We get 0.1915. So that means that there is that 19.15% of all values lie between 0 and 0.50, right? So this is the white area here, and that's what's represented in the meat of the table. So all we have to do then is we have to add 50% to this. So the probability of z being less than or equal to 0.05 is 0.5 for this white area here, plus the 0.1915. So it's 0.6915, right? So that's what we get. Oh, wait, that put zero. What did I do here? 0.0, oh, 0.05. So, 0.05, not point. It was 0.05, not 0.50. 0.05, aha. Good thing. You need me to make mistakes. It's actually good for it. 0.0500, 0.01, 0.02, 0.03, 0.04, 0.05. So the gray area here is, or blue, whatever that is 0.0199. So we're going to add that to 0.5, but 0.50199. So that's your answer there. I was just testing you, right? I was just testing you to see if you got that right. There it is. All right. So we've got 0.5199, and we can round it up to 0.52. Okay. So the next question was, what's the probability that z is greater than that value, right? So we can use the rule of complementary events. So a complement of what we found was basically it's the opposite. And we know that the probability of all elements in the sample space have to end up equaling 1. So in this case, we only have 2 elements in the sample space, although this is a continuous distribution and we have an infinite number of elements, but we're breaking it down into 2 elements here. Either it's less than or equal to 0.05 or it's greater than 0.05, right? So those are the 2 complementary events. Because we have the probability of 1, its complement would be 1 minus that probability. So 1 minus 0.52 is 0.48. So our answer to the second part of that question is 0.48. So how would you tell this to somebody? If somebody asked you, would say, well, 52% of all individuals scored less than this random student, and 48% scored above the random student. Okay? Pretty sweet stuff. Item number 2, another random Pennsylvania student took the SAT test and scored 521. So this person was below. What's his percentile score? What's his percentile score? His percentile score. Okay. Okay, let's see. So what's the probability scored? Okay, so percentile score, and then what's the probability that somebody scored above? Ooh, what's the probability somebody scored about the second student? Above. It should be above the second student. Above the second student, but below the first student. See, this is where it gets tricky because you got to be able to do all this stuff. All right. So we got 521 here for the second one. All right. So we got our x value, specific value of our variable is 521. So we want to know what's the probability that x is less than 521, less than or equal to 521. So we plug everything into this z formula or z equation. I like the word equation better than formula. Formula makes me think of something that babies drink. Right, Piper? Yeah. So Piper agrees with me. So 521 minus 531 divided by 111. So we're using the same mean and standard deviation because the same population. This is one of the few places where you have all the population values, like in a standardized test, because all the data are collected and we always have all the data available. Look at minus 0.0901. So our question is, what's the this is going to be fun for me at least. I hope it's for you. What's the probability that z is between 0 and minus 0.09? And then our question, of course, is what's the probability that z is less than or equal to minus 0.09? So you're thinking, wait a minute, but there are no negative values. And I know how people think. I may have told you this 100 times, but you're thinking, what we don't have any negative values in the table, so we only have positive values. Then you remember, wait a minute, everything's symmetrical. So the probability that z is between negative 0.09 and 0 is the same as the probability that z is, oh, let's see, that z is greater than 0 but less than or equal to 0.09, right? It's the same thing because of symmetry. So we can go to our table and look for 0.09. 0.0, and we go all the way to the 9, right? Right here. So this is 0.00123 all the way to 9. And we get 0.0359, 0.0359. So that's this area here, but if you flip it on the other side, that's what we get. And what we're looking for is the white area that's equivalent to this area, right? So the easiest way to do that would be to subtract whatever we found here, the 0.0359, right, from 50. Let's do that. Where are we? Here we are, right? So we had 0.0359 and we subtract that from 0.5 because again we're looking to the area to the left of that gray or whatever that color is on the left side of the distribution. Just by definition, that's what a percentile is, less than or equal to a certain value. We get 0.464. All right, so that's the probability that's less than or equal to our student, right? Okay, and what's the probability that someone scored above her score? So that would be what's the probability that z is greater than negative 0.09? That's going to be using the rule of complementary events. It'll be 1 minus 0.464 or 0.536, which we could estimate to be 0.54, right? So 54% of people scored above this youngin, or wean, as they say in Ireland or Scotland. And 46% scored below, at or below this individual. Sweet. All right, I think that's all I had for that one. Let's see. Let's keep on going. All right. Oh, I didn't do the between. Did I do the between here? So the between, I thought I did the between. How dare I? Did I not do that? Well, I'll just show you how it's done. I don't have access to a right. I told you I need this writing tablet. So the probability of being between those two scores, basically what you need to find is the probability of being less than or equal to the first, or the higher one, right? The higher one was this individual, because this individual scored 537, so she scored higher than the second individual. So the probability of being less than or equal to her score, probability of being less than or equal to her score was 52%, right? We calculated that. And the probability of being less than or equal to the other person's score was 46%. So really, if we want to know what's the probability of scoring above the second individual but below the first individual, it would be the difference between the two. So 0.52 minus 0.46, or there's a 6% difference, right? So what's the probability that someone scored above the second student but below the first? 6%, right? 0.06. It's just the difference between the two. That's the cool thing about doing these problems is that you just want to visualize that curve. I would actually draw it and then just, do things visually. If you're a visual person, just draw them and do it. Just draw it. All right, let's go to number 2 here. Okay, real number 2, Roman numeral 2. I don't know what you guys learn anymore, but there's Roman numerals like 1, 2. I forgot to change this to one of you all. I tend to like to change the names to people in the class. But this is from the last time I taught. Dr. Badstubner and Doctors Badstubner and Jackson are completing a study to assess the predictive validity of their new home testing kit for disease D. Disease D has a 9% population prevalence. They are assessing their testing kit in Greater Milford, which has a population of 543,000. Initial testing found that the sensitivity and specificity of their home testing kit is 0.89 and 0.92 respectively. Somebody actually once asked me what that is, so I shouldn't assume that everybody knows. When you say respectively, you match things. Sensitivity is 0.89, specificity is 0.92. As you recall, what you want to do to fill this in is you always start with the prevalence. So the prevalence here was 9%. So I'd multiply 0.09 times 543,000. I'd write in the 543,000 here and then take 9% of, what is it? 9% of that. So that's 48,870. And then you work your way from there. So then knowing the sensitivity, I would multiply 0.89 because sensitivity is the probability of testing positive given you have the disease. So it's 0.89 times 48,870, which gives me this value, 43,494. And the specificity, well, it's the probability of testing negative given one is disease negative. So it's 0.92 times this value here. This is the difference between these two, right? Since I calculated the prevalence, I just subtract the number who have the disease from the total, and I get the number who don't have the disease. Then I use this to get my number of true negatives. Okay, and you just complete that as follows. To regarding recalculate the sensitivity. So we have the sensitivity, so you know what the answer is, right? But you got to show me that you know how it's done. So you take the values and plug them into here. That's what I'm looking for. I want the values. I don't want you to just give me 0.89 because you're probably thinking, well, what the heck? Oh, I got a freebie. No, you didn't get a freebie. I just want you to actually show me that you know that will be 43494 over 4887. You see Piper's like really chiming in here. That's 0.89. Same we do with this specificity. Calculate the PPV using the table. So what I mean there is that you're going to show me how you do it if you have the tabulated values or tabular values. Specificity by, sorry, PPV by definition is the probability of having the disease given you test positive. So we know that 83,024 tested positive, and of those, we know that 43,494 have the disease. So by definition, for PPV, it would be 43,494 divided by 83,024. That's what I mean by using the table. That's 0.524. I'm going to say recalculate the PPV using Bayes' equation. So that now we use Bayes' equation. As you recall from our lesson, that's the probability of being disease positive given you test positive. And using a combination of the multiplication rule, the addition rule, we can actually calculate this value. The denominator is the total probability of testing positive because you can test positive and be disease positive, or you can test positive and be disease negative, right? So that's what this denominator is. And because of the addition, we're using the addition. We're using the addition rule because of excuse me, we're using the addition rule. Yep, we'll just figure that out from there. So you use this equation and you just start plugging things in because we have this sensitivity is 0.89. We have the prevalence, 0.09. Then remember that's repeated in the first element here, right? That's the same as this. And then here you have the probability of testing positive given your disease negative times the probability of being disease negative. So the probability of testing positive given your disease negative is a false positive, which is the complement of the specificity, right? Because specificity means you test negative given your disease negative. So either you test negative or you test positive. So those are complementary events. So it's 1 minus 0.92, which is 0.08. And the probability of being disease negative is a complement of being disease positive. So there's a 9% prevalence, right? So 1 minus 0.09 is 0.91. You just do the calculation and they should equal. If not, you did something wrong. All right, let's move on to the third one. Imagine the probability of owning a pair of biker boots. I have some of those. Forget to call it engineering boots. Is 0.07. The probability of owning a pair of cowboy boots is 0.20. If the probability of owning a pair of biker boots and a pair of cowboy boots is 0.04, what's the probability that one owns either of the two, right? So these are all word problems. When you say, what's the probability one owns either? So you say, oh, it's either or. Or, I remember that's addition, right? So you're going to use the addition rule here. So it's going to be 0.07 plus 0.20. I probably wrote it down here somewhere. Yeah, 0.07 plus 0.20 minus the probability of their joint occurrence, because apparently 4% of people own both. I'm not a big fan of cowboy, the pointed cowboy boots. I used to have a really cool looking pair, but man, they hurt. So 0.27 minus 0.04 is 0.23. So that's your answer there. Okay. Is owning a pair of cowboy boots independent of owning a pair of biker boots? We know they're independent if this holds. So the probability of owning cowboy boots times the probability of owning biker boots would equal the joint probability of owning both, right? We already know that's 0.04. So the product of these two has to equal 0.04. However, it equals 0.014. Since they're not equal, they're not independent. Okay? Read through that to understand why. Number five. Number four or five. Did I skip something? What is why? What did I skip? Did I skip some? Oh, here it is. No, here's four right here. That's the line is right there. So what proportion of the population, what proportion of, shut up, Piper. What proportion of population value? See, he wants to like be involved all the time. He's probably doing math. In his parrot, he's very, very smart. What proportion of population values in a standard normal distribution are above one standard deviation below the mean? Don't you love when I do that? That's like tongue twister. I can barely say it. What proportion of population values in a standard normal distribution? So this is using the empirical rule, right, Piper? Yeah, Piper likes the empirical rule. Actually, he prefers Chevy-Chev's inequality. What what proportion of population values in a standard normal distribution are above one standard deviation below the mean? All right, okay. One standard deviation below the mean. We call it by the empirical rule, 68% of all values are between plus or minus one standard deviation of the mean. So from 0 to 1 standard deviation below the mean is half of that, right? Half of 68 is 34%. All right. All right. So you can do two things. You can add that 34% to 50%, right? The proportion that's above the mean, and you get 84%, right? Or if you want to, you can do 1.5 minus point, oh my God, 0.34, right? Which would be 0.16, and 1 minus 0.16 is 0.84. I don't, either way, it's just a matter of visualizing that difference. You got to visualize it. So play around with those. I love giving those problems in exams. Cool. All right, number five. Number five. Using the data in the table below, calculate the sample variance and the standard deviation. Sample variance and it should be sample standard deviation. I would use the shortcut variance equation, which is right here. You can always remember, I always remember this because it's always the sum of the x's squared minus the sum of the x's squared. That's the way people say it, divided by n. And that whole sucker is divided by n minus 1. You know, there's 10 values, so n minus 1 is 9, n is 10. And then here I gave you everything you needed pretty much, right? Here's 361. That's the sum of the x's. And at some point, you're going to have to square that, right? And I gave you the sum of the x's squared. So I squared all these suckers for you. I gave you 134.03. So you just plug everything into the equation. If you plug everything in correctly, you get the right answer. There's a saying in stats, junk in equals junk out. So if you put the wrong things in, you'll get the wrong answer. Standard deviation is merely the square root of the standard, square root of the variance, which is 6.42, I believe. That's what it looks like to me, 6.42. It's my handwriting. Again, I can't wait to get this tablet. I've been looking for one. I finally found one that works. What I need is a direct translation from the tablet on screen, and that wasn't as easy to find, but I found one. I forgot who makes it. It's on my list of things to get. I also have to get a camera, a video camera. I'm going to start making skiing movies. All right, Dr. Benley is counting the number of patients entering. Oh, sweet. This sounds like a Poisson problem. So how do you know which equation to use? Good question. You get clues, right? Dr. Bentley's counting. Ah, counting. That sounds interesting. Counting. We know when we calculate probabilities, when we count, it could be either a Poisson or it actually could also be a binomial because we count the number of successes, right? Okay, let's take a look at this. Dr. Bentley's counting the number of patients entering a clinic per 12-hour period. Okay, that sounds interesting. I'm getting this time constraint. Okay, let's see. He found that the average number of patients entering the clinic is 96. He's worried he's not properly staffed in case of surge of patients. Wow, that's a toughie. Um, properly staffed in case there's a surge of patients because of the apparent outbreak of disease D in the community. What's the probability that he'll see 8 patients an hour? And the reason I said, wow, it's a toughie is because I gave you the rate. So now I know it's a Poisson problem because we're talking about a rate. How many people enter per 12-hour period? It's 96, right? But then I asked you for what's the probability that he will see 8 patients in 1 hour, right? In an hour. So I'm not interested in the rate per 12 hours. I'm interested in the rate per hour. So the first thing I have to do is find my lambda. Lambda. There's a movie, was it a Revenge of the Nerds, where the main characters were tri-lambs. Tri-lambda. So lambda is a rate parameter. By the way, in terms of the natural parameter, it is a natural parameter for the Poisson distribution. So we need it for an hour. It's 96 divided by 12 equals 8. So my French students, I know I have a couple French students here. This is like for you, the Poisson, the fish distribution. Actually, somebody's name, but it's still fish, right? I'm hungry now. Okay, so lambda's 96 divided by 12, which equals 8. All right, so that's our rate parameter. Interesting that we asked the first one is what's the probability that he will see 8 patients in an hour? So we just plug this into our equation for the Poisson, which is lambda to the x. X in this case is 8, right? So that's why I'm asking what's the probability of seeing 8 participants? Lambda to the x, e to the negative lambda, which is also 8, divided by x factorial, which is also 8. A lot of 8s here. All right. And I get 0.140. Okay, 0.140. So the probability of seeing 8 patients in an hour is 14%. All right. What's the probability of seeing 11 patients in an hour? Here I do. I like to play around with this. Probability x is equal to 11. Again, we got lambda to the x, lambda to the 11, 8 to the 11, e to the negative lambda, divided by x, which is 11 factorial. I got 0.0722. You can't leave well enough alone, right? I just cannot leave well enough alone. So I have to start playing with all these. I play with all these rules, right? Because this is the kind of stuff you see in real life. What's the probability that he'll see 8 or 11 patients per hour? All right. So 8 or 11 patients in an hour. We have probability of seeing 8 patients or 11, which is the probability of seeing 8 plus, because either or, right? Now, no, here's what I did. This is something interesting here. I did this on purpose, right? I applied, I used the entire addition rule. If you recall from an earlier lecture, I discussed that the or it might be the same lecture. That was the earlier one on probabilities. I discussed what's the in these different probability rules. I said, how do we get the probability of either of two mutually exclusive events? Well, you can't have both 8 and 11 patients. It's either 8 or 11. So I still stuck this here because this is still the addition rule, but this probability is 0 because it can't happen, right? So you'll notice that I say minus 0. So probability 8 plus probability 11 minus 0. I get 0.212. So there's 21% chance, right? 21% chance that you could see 8 or 11. So that's more, it's higher because there's two possibilities there. Sweet. Number 7. Now this is where I start getting creative because I know it's lanternfly season. Imagine that Jessica is inspecting the large hammocks on the quad for spotted lanternflies as part of an assignment for her environmental sciences course. If the average number of spotted lanternflies landing on the hammock is 13, okay, the average number is 13. So again, we have a rate. That's how many land on a hammock. It doesn't have to be per time. It could be per space or anything like that, right? That's what's cool about using the Poisson, the fish. Flies landing on a hammock is 13. What's the probability that there are 9 spotted lanternflies on the hammock? Okay, so this should start being easy because I gave you I gave you I gave you the lambda, which is 13, right? And I asked you for what's the probability of 9. So this should start being, oh, okay, this is easy. Lambda to the x, so it's 13 to the 9, times e to the negative lambda, so it's e to the negative 13, divided by x, or 9 factorial, and I get 0.066. Woohoo. If the probability of finding a lanternfly wearing a bucket hat, you see that, lanternflies get these mini bucket hats, is 0.24, and there are 27 lanternflies on a blue Adirondack chair, what's the probability that you'll find 10 of them wearing little bucket hats? Wow, what the hell's wrong with me here, right? So the probability is 0.24. So it's the probability of wearing. Oh, okay. So this is a different problem. Okay. So this is not, and I was for a second because my mind works that way, right? This isn't a this isn't a problem. That's a Poisson problem because there's there's some differences here. So let's look at this again. Tania is in the same course as Jessica. Instead of counting lanternflies on a chair or hammock, she's interested in finding spotted lanternflies wearing tiny bucket hats. Okay, so let's see here. If the probability of finding, so this is the probability of success, right? So I'm giving you a probability. A probability of success uh, is 0.24, and there are 27 lanternflies on a blue Android. So I got an N. So I'm thinking, okay, it's a little different because in the problem with the Poisson, I wasn't getting an N. In fact, I wasn't getting a probability either, right? So I'm getting two pieces of different pieces of information, and that should tell me, okay, maybe this isn't a Poisson problem. What's the probability that I'd find 10? Oh, you want to know the number of successes. The probability of finding 10 successes, 10 lanternflies wearing bucket hats. So I'm not, while there are some counting involved here, 10 of these, but this to me doesn't sound like a Poisson problem. It sounds more like a binomial problem because I want to know what's the probability of a certain number of successes in n independent Bernoulli trials, yes or no trials, right? So yeah, that's it. So we know the p is 0.24, the n is 27. And we can plug this into our binomial equation, right? Our binomial probability equation. So what's the probability x is equal to 10? We have n choose x, right? That's our binomial coefficient or a choose function, if you will, is p, which we know is 0.24 to the x, times q. Remember, q is the same as 1 minus p. We just use it for shorthand to the n minus x. So here we get 27, choose 10, and we just work this out, right? Carefully. And if you recall, this here is n factorial or 27 factorial divided by x factorial times n minus x factorial. Use your calculator wisely here, but notice how I'm showing the work. This is what I want to see. You can do all this stuff with your calculator. That's fine. You still got to show me the work. I get 0.0504. So this is a probability seeing 10 of these little guys. What's the probability that no spotted lanternfly of the 27 is wearing a bucket hat? Okay. So that's probability that x is equal to 0. So that's an easier one to calculate. That's always this coefficient is always going to equal 1, right? Because you got n divided by n, right? Because remember, this second component is n minus x, and x is equal to 0. Okay, so we get 20.24 to the 0 is going to be 1. So basically, it's just doing 0.76 to the 27. We get 0.000605. What's the Now, this is one that I love doing. What's the probability that of at least one spotted lanternfly out of 27 is wearing a bucket hat? The very what's the word? Literal minded student might go, okay, probability of what's the probability of 0? What's probably at least one? I'm sorry, what's probably 1? 2. So you just add one probability of 1 plus the probability of 2 and do all the way to 27. It's a lot of handwriting. My hand would be cramped doing that. But instead, the wise person says, wait a minute, wait a minute. The probability of at least 1 is just the complement of the probability of 0, and we already calculated the probability of 0. We know the rule of complementary events, so we just subtract this from 1 and we get 0.999. So basically almost 100% chance. So what's the probability at least one spotted lanternfly out of 27 is wearing a bucket hat? It's almost 100%. Okay? It's just using your noggin. Piper taught me how to do that on one of his days off. All right, thank you all. Have a wonderful day. I'm going to post this. This is a good video. It's a good video. All right, thank you. And if you haven't subscribed yet, remember, extra credit for subscribing. If you look at your extra credit and it says 5 rather than 10, that means you only subscribe to one of the channels. Just subscribe to both. Hey, there's no right or wrong to that. That's just like extra credit. All right, thank you. Bye.